So when we're doing circular motion is a good time to talk about in a little more detail sort of a philosophical topic of Newton's laws. And the reason this is a good time is because this business of centrifugal forces, which we uh, talked about briefly a few videos ago. So the first question you might ask yourself is, does it Newton's first law just seems to be a special case of Newton's second law, doesn't it? Newton's second law says that the force is equal to the mass times the acceleration. Newton's first law seems to be just a special case of uh, Newton's second law when the acceleration happens to be zero. It sort of seems that way. Once you learn Newton's second law, Newton's first law seems redundant. But in fact, Newton's first law plays a much more important role in physics than simply the law of inertia, the fact that objects which experience no net force are in equilibrium. And so let's ask ourselves the question, are Newton's laws always true? We always tend to think of a law as being something which is always true. Once you find a law, you think, okay, now I've got the way something is always going to behave. But in fact, Newton's laws are not always true. They're only true if you happen to be in a coordinate system, which is referred to as an inertial frame. There's that word inertia poking in again. And in essence, what Newton's first law really does for you is define what an inertial frame is. An inertial frame is a frame of reference. It's a coordinate system. It's where you are, in which Newton's first law is true, in which an object with no net force on it does not accelerate. Now, can you think of any situations where an object with no forces on it accelerates? Or can you think of a situation where an object does not have zero net force on it and does not accelerate? Well, let's take the second case. Imagine that you are sitting in a car, stopped at a stoplight, and when the light turns green, you put your foot down on the accelerator and you start accelerating forward. Now, in your frame of reference, what do you experience? What you experience is that you feel like you're being pushed back into the back of your seat. But you're not really. You're just feeling the back of your seat pushing forward on you. So in your frame of reference, what are all the forces on you? One force is, maybe we should try to draw a little picture of this. Okay, so here is the seat of your car, and here is you. Okay, and what forces do you feel? Okay, well, you feel your own weight. You feel the car seat pushing up on you. So far, everything is fine, but you also feel the car back pushing you forward. So let's just call that the force F. Okay? Now those forces, N and mg, add up to 0, but F is not 0, and therefore Newton's first law is false in this car. So this car, which is itself is accelerating, is not an inertial frame of reference because Newton's first law is false. Okay? So let's now see how that applies to the kind of thing we've been studying recently. So I'm going to imagine that I'm going to ask you to imagine that you're sitting in a on a merry-go-round. The merry-go-round is going around, and you have a little pendulum with you. And the little pendulum, when you hold it in front of you, you find it swings out to the outside. You could imagine this happening, right? If the merry-go-round were going very fast, you would feel a force yourself trying to push you off. Okay, there is no such force, but that's the way it would seem. So here is the pendulum, the center of the merry-go-round I have made over here off to the right. Okay, and so what you're going to find is that this makes some angle theta with the vertical. It doesn't hang straight down. And so you say, well, what are all the forces on the pendulum bob? Well, there's its own weight, mg, down. There's a tension in the string T, like this, and that's it. There are no other forces. Okay? Therefore, the merry-go-round is not an inertial frame of reference, because here's a situation where, in this frame of reference, there are no accelerations, and yet the forces definitely do not add up to zero. So, what do we do about it? Well, we simply say, well, yeah, this is not in equilibrium because we know it's going around in a circle. On the other hand, suppose that we are stuck on this merry-go-round and we want to do Newtonian physics there. Okay. For example, if you think about it, being on the Earth is like being on the merry-go-round, because the Earth is spinning around on its axis and the Earth is going around the sun, so it's a sort of complicated merry-go-round. It's a merry-go-round on a merry-go-round and so forth. Okay, and so in fact, if you think about it in detail, the Earth is really not an inertial frame of reference because the way that because you're accelerating. The frame is always accelerating. How can we make this merry-go-round, how can we do physics on the merry-go-round using Newton's laws, which are in fact blatantly false? And the only way to do that is that you invent some force which makes the whole system be in equilibrium. Okay, and so what you do is you say, okay, I'm going to make there be a force like this, and I'm going to call that force, let's just call it F. Okay, this is what we call a fictitious force. Okay, and in this case, this fictitious force has a name. Okay, it's called a centrifugal. Centrifugal force. Okay. And like I say, it's fictitious. It doesn't really exist, but it sure seems like it does. When we're sitting on the merry-go-round, we sure feel ourselves being pushed toward the outside, even though that's not actually happening. There is no real force there. So this is what the centrifugal force is, and now it's pretty straightforward to figure out what the centrifugal force is. The sum of all the forces in the y direction has to be 0, okay, and that's going to be equal to minus mg plus t times the cosine of theta, and the sum of the forces in the x direction has to be 0, and that's equal to t sine theta minus f. And so F has got to be, in this particular example, the centrifugal force, the force which you invent, is T sine theta. And we also know that mg has got to be equal to T cosine theta. And I've made my point, I think, that we now have two equations and two unknowns, and so we can find the tension in the string. And and theta, and so therefore we find out what F is. Okay? So, Newton's first law is important in that it defines what an inertial frame of reference is. An inertial frame of reference is one in which Newton's laws are true. Newton's first law is true in particular. And once you have found one inertial frame, any other frame which moves with a constant velocity with respect to that one is also an inertial frame of reference. Okay, so this was just sort of a little enrichment video.